Welcome back to week number 11 during instrumentation. Here I've just finished a video where I did this problem. Here's another problem that's using the same figure. All right, so accelerometer consists essentially of a box containing a mass spring system with a no natural frequency right here. So all right up at the top, the natural frequency is 2,200 hertz. It's a pretty high natural frequency. Box is rigidly attached to the surface that is moving according to this right here, right? So this is the ground is shaking or the machine is shaking, this is attached to. If the amplitude of the motion of the mass relative to the box times a scale factor, omega n squared, is used as a measure of the maximum acceleration, this guy right here, of the vibrating surface, determine the percent error when the frequency of the vibration is 600 hertz, right? So I have a forcing frequency of 600 hertz. Now, they're calling it an accelerometer, but we can see right away that it's kind of a, we're not dealing with the, yeah, trying to think if I can say this the right way. We're going to continue to use the Z term. I think that's true, right? So I looked at the solution, and I think I want to do it both ways. Actually, to tell you the truth, but let me do it both ways. I can do. I have the technology and I have the time. I guess I have the time. So we'll find an R for this, and so we're gonna find that that's going to be the forcing frequency over the natural frequency, and that's going to be 600 divided by our 2,200. Okay, which is going to be 0.2727, and that's pretty darn close to that 0.2. So I'm very tempted to say, okay, let's say that this is an accelerometer, right, and use the equation. First off, I will do the velometer or vibrometer equation, right? So we have the z over y is going to be equal to r squared over 1 minus r squared, right? So because we don't have any damping. I said that in the previous example, so I should mention why I'm writing this as no damping. And the equation that I'm using for this on the first one to just kind of explore onto the thing is this one right here, the vibrometer error term. We're going to do that one first and see what we get. Let's see how different the value would be when we use the fact that we are going to separate that r squared into parts that we distribute here. So this is the accelerometer's acceleration, and here is what we're measuring's acceleration, and that would be considered the accelerometer error term as opposed to the overall vibrometer one. All right, so let's get this back. Okay, so if we do that, we get 0.2727 squared divided by 1 minus 0.2727 squared. And our error, let's see, and therefore we get a value out of this. It's actually not quite the error because we're getting a 0.08036. So is this a correct one? I don't think so, because usually we're going to get something that's greater than 1. Part of this has to do with, I think, that we're on the other side of this curve right here, right? So when we were over on that side, we were going to get something small, and over there we're going to get something greater than 1, right? So over here we're less than 1, over here we're greater than 1. I think we would prefer to have the accelerometer relationship right here, as we see when we plot that out. that we have like a sort of a straight line in this region. The problem that we have is that we have no damping going on. So we could have a crazy large answer. Like, let's look right over in there. That's not zero damping. This is zero damping right there. So we have zero damping right there. We can see that it's got an upward swing, and I didn't even bother to put it into down here. But let's see what our error term is without damping. We really do need damping in here. So here is our alternate solution to this. We're going to have z double dot y double dot. And I don't know what the results of this are going to be, by the way. So this is, we got rid of that top term. So we have 1 over 1 minus 0.2727 squared. And I'd be nervous if I was me, because I think we're going to get something messed up. So let's go 0.2727, square it, subtract it from 1, and then take the inverse. All right, not too bad. We get 1.0803, right? And the original problem I did get, so you can see that it's actually pretty darn close to what we have here, except that there's a 1 on top of it. So I would say that the answer to this right here, in terms of our error, is equal to 8.03%. And yeah, so it's an accelerometer problem. It is an accelerometer problem, it turns out, because we're talking about something that has a very low R, which is more suitable to accelerometers. And if we had some damping involved, we could get that error down a lot more. Let's take a look at another example.